Okay, everybody finished the quiz? Okay, perfect. Can you hand all the way to the right? I'll pick up from the side. David. Okay, everybody. So the quiz would be a good example to let me understand everybody's understanding about lattice theory. So let's begin today's lecture. Today I'm excited to expand what we have learned from lattice series to a more general theory that's relevant to polymer science. And that specific topic is actually called Flurry Huggins theory. This is the most important concept in polymer physics from my perspective. So how does polymer interact with solvents? Up to now, last time we only talked about lattice theory concerns about what? When we fill in these white dots with these red dots, we actually do not have any, we assume though they are similar size, and so that we can fit in these empty spots in the lattice or grid. But I think about for polymer, that will not be the case. I cannot argue a polystyrene with a molecular weight about 20 kilodalton will be the single solvent. So something has to change in today's lecture to fit in or modify the theory about polymer science with respect to the solvents, okay? And that's kind of the beauty of what we do here in the polymer science department. We concern about polymers, so naturally we want to adopt the lattice series to Flurry Huggins theory. That's what we're going to do today. We're going to cover how do we understand the mixture of a polymer and a solvent. It's one step forward, and down the road we're going to talk about the polymer. Basically, we can envision the polymer will be a special case in mixture, right? Polymer just connected moleculars. So we take one step to replace one part of the dot to be a polymer. The other keep as solvents. Then down the road, we're going to replace both solvents to be polymers to look at the polymer blend. So let's take a look at again. Is this looks like shaky to you guys? Yeah. Okay. Hopefully this will stop since something is going on in the building. So what we covered in last lecture is talk about the lattice theory. Lattice theory basically tells you how does polymer, how does solvents molecule can be mixed and can be understood. So in that particular part of the lecture, we cover what's the free energy of mixing in any given system. So this is a universal. Delta G equals to delta H minus temperature multiplied by delta S. Again, free energy changes. Delta means changes before and after mixing. Delta H means changes of enthalpy. We covered that. Remember how we talked about N11, N12, etc., the pair interaction parameter. And we later talked about how does chi parameter with respect to delta H. Delta S we also cover in the last lecture. That's entropy. So how many different configuration states are possible when you mix solvents. So that's what this delta S value is. And we came to conclusion in the mixture of two solvents. We can reach the conclusion that delta S mix, the entropy change, will be equals to minus R. R is a gas constant. It's just a value that everybody knows is 8 point something. It's not on the top of my head, but there's constant. You can look it up.
314.
Yeah, okay. Thank you. Thank you both. N1, how many moles of your polymer, solvents A or solvents 1, Lowing. X1 is molar fraction of that X1. So if we mix 1 mole with 3 mole of material, this will be equals to 1. This will be equals to 0.25. Okay, and the other part. So consideration entropy change in for the solvent 1, solvent 2. The enthalpy change is interesting because we defined a new term that is what this chi parameter is, or Flurry Huggins parameter. This basically considers how does Flurry Huggins parameter changes upon mixing. And we can apply these HS into the top equation as I underscore with the red line. So this will tell you whether the delta G change for the whole material system. And as shown here, that's a lattice theory. And there's actually 2 ways people want to present this. This considers the whole system. And sometimes it's easier to think about what happens per lattice sites. The difference between these two is we're going to divide this by how many lattice, total lattice possible. Okay? What this means is if we have 2 mole of lattice, then we're going to normalize by 2 mole. And if we normalize that, this is just going to be divide by n1 plus n2 for across the board, which will change one thing. n1 divided by total m1 plus m2 will be equals to x1. It will not change the conclusion if the polymer will mix or not. That determines by if the delta G is positive or negative value, right? We talked about when delta G is negative, it will spontaneously mix. So if you normalize by a value, it just changes sign. Negative value is still going to be negative value, but it's considered per site. And the beauty of that is now you can normalize it to write down R will be converted to K because divided by Avogadro constant, R divided by that will be equals to K Boltzmann constant, KT, and given by this equation. So one note, this is a sort of called mean field results. The interaction and energy were taken to equally. Okay, that means you average everything. Mean field, it means it's average every single sites. Okay, this only works for low molecular weight components with approximately same molar volume. This basically tells you the limit of lattice theory is you have to, your solvents or your mixing has to be really low molecular. Otherwise, the lattice doesn't make sense when you can squeeze a large molecule in a lattice, which is the reason we're going to cover it today. So let's do an exercise about how delta G can be relevant to other parameters. So for example, let's use mixing 1 mole of toluene with 1 mole of cyclohexane, assuming a chi, which is given by the textbook or handbook. So this will be equals to 0.24. Will they mix? So how do we judge? Well, 1 mole of toluene and 1 mole of hexane will mix is given by this delta G value. Okay? So now let's take the equation what we have in delta G mixing will be equal to exactly what we have in the lattice theory, N1, N2, and N1x2, and this is the entropy contribution, this is the enthalpy contribution, right? So let's plug in the value. N1, we talked about 1 mole, so N1 will be equals to 1. Log in x1, what's the volume fraction of that? We mix 1 mole of A, 1 mole of B, so x1 will be 1 divided by 1 plus 1 will be equals to 0.5. So that's where this part comes from. Log 0.5 will be the entropy contribution of the toluene, and you have equally N2 will be equals to 1, and x2 will be equals to 0.5. That's the entropy contribution from hexane. This is how the chi parameter or enthalpy comes into play. Equals to N1 is equals to 1, x2 will be equals to 0.5, and you have a chi parameter of 0.24 as outlined in this problem. So let's plug in the values and do some calculation. Log in 0.5 will be equals to minus 0.693, And you have another contribution for other half, and that's the chi parameter. So if we did this, we will reach the conclusion that delta G will be equals to minus 1.24, as we can see. This mixture will be spontaneously, as the system will reaches a lower energy states when delta G is negative. As you can see, for this process, one of the key things is we have entropy is much bigger than entropy. So in this case, we can mix them just because entropy wins the battle. However, let's say if our chi increases by a factor of 100, of course, in reality, that's not going to happen, but think about that. If you have some very unfavorable systems, chi is 100 times bigger, this now will be turns to value of 12, will be much bigger than this particular value. You don't need a factor of 100 to make the entropy turns to be larger than entropy turn, right? Probably, let's see. If you make it maybe 15 times, this probably entropy will be bigger than entropy. So your system is no longer favorable or spontaneously mixed. Okay? So, which means if you have a chi about 1.5, then you're not going to be able to mix them. Any question here for this particular example? So that will cover everything about lattice theory, okay? So now we're going to talk about, look at top left, Flurry Huggins theory. Lattice theory and Flurry Huggins theories are very similar, with the exception that Flurry Huggins smartly expanded what we have learned from lattice theory to polymer system. So I want to ask everybody a question. What would it be changing in what we have shown in entropy, enthalpy, and mixing? Because fundamentally they are governed by the same principle. We need to consider delta G. We need to consider enthalpy and entropy when we mix. For example, we can think about this is a polystyrene in the matrix of a hexane, let's say. Okay? So what's the difference compared to toluene hexane versus a polystyrene hexane? We have kind of show a figure here, but anyone want to make a motion to make some suggestion? Well, we need to consider differently here.
Because there's less combinations, because in the polymers they have to be sequential.
Perfect answer. Excellent. Entropy will be different. Entropy will be altered because in the solvent, when we do the lattice, what we have done is basically show we can fill one solvent molecule, then the next one can be randomly placed in the lattice, right? We don't necessarily need to put, let's say, next black dots next to it. We can just pick another one because each molecule is independent. Well, in the polymer, it's not the same. The polymer are more governed by the connectivity of the nature of these covalent bond in the backbone. I cannot stretch, let's say, this polystyrene, the next bond to be here. It doesn't make sense. It has to be in the Flurry Huggins. When you fill a polymer chain in the lattice, the next dots has to be connect to the first dots. So let's say this is how you fill a polystyrene chain inside a lattice, as we talked about. So this connectivity is unique to polymer, and this chain connectivity impacts greatly how the entropy is coming into play. Okay? We're going to discuss about that in more detail. But for now, I just told you the fundamental reason, a fundamental difference between lattice theory versus Flurry Huggins theory. Flurry Huggins, basically, we consider a structure with more interconnected molecular system. Okay? And Christian kind of mentioned this is going to be a drop entropy. So we just need to understand, how does connectivity impact the drop of entropy? right? So in this case, polystyrene and hexane, will the hexane's entropy contribution to mixing will be changed? Any guess? I see many people shaking their heads. It will not, right? That's a good answer, because when if we consider how we feel in the hexane, it's still pretty random. You can achieve what we have talked about in the lattice series, no matter how we feel it. The changes in the entropy with respect to the mixing will not differ a lot for hexane. So we know how that would work. So how about in the polymer? Then we need to do something to keep the polymer fit into the regular lattice series. And the trick we do is we just say, okay, now I compare hexane. It's much smaller, but your polystyrene with a given molecular weight will be much bigger. How do I feel a polymer in a lattice? This can be done by normalizing the polymer volume with respect to the hexane. Let's say your polymer is much longer and bigger. How much its occupied volume needs to be normalized by the solvent molecule. So in other words, how long this will be connected will depend on two things. Unit lattice size, how each lattice size occupies a certain volume, and how much volume your polymer occupies, which is proportional to degree of polymerization. Okay? So in the simplest case, we just make an assumption that how many lattice of your polymer will be occupying will be equals to degree of polymerization n. Okay? In this case, we made a very naive and simple assumption. Your monomer of your polystyrene, let's say, your styrene monomer will occupy the same volume as a hexane, or same as toluene. So that's where styrene monomer, the next styrene monomer, and this you can visualize as, in this case, let's call it a hexane if you're mixing toluene with hexane. Okay? So any questions so far? How we consider and treat Flurry Huggins series of a polymer with the solvents? There's two assumptions we just mentioned. We need to consider a size difference between these two systems. Okay? And how we treat it is to consider monomer to be the same size. It changes a couple of things in terms of describing the volume fraction. In one case, in the x1, x2, in the previous case, in the lattice series, x1, x2 is the volume fraction for polymer, the solvents A and solvents B, right? Now we call it slightly different. We're going to call it phi 1 and phi 2. What's the difference between phi 1? It's basically saying that's going to be given by the volume fraction of the solvents, okay? That's going to be the volume fraction of the polymer. Solvents, polymer, and combine the volume, they're going to be equals to 1. Okay, let's say I mixed 1 mole of polystyrene and 1 mole of hexane. The phi 1 and phi 2 is no longer equals to 0.5. Did you guys get my point? In case of mixing of toluene with hexane, because you assume they are equal volume, so it will be very simple. 1 mole of toluene, 1 mole of hexane will be equal to equal volume fraction. So in this case, 1 mole of polystyrene versus 1 mole of hexane. The polystyrene is occupying much bigger volume. So we need to define this term. How much volume we have in hexane will be equals to this. Given the symbol volume, this is the volume of each lattice sites. So you can think about a unit volume. M1 is basically number of solvents. So the total volume for the solvents will be given by how many of solvents molecular. M1 multiplied by unit volume. Okay? Polymer volume. And we already mentioned that the polymer gonna be each lattice is occupied will be V0, that's unit lattice volume, multiplied by how many number of polystyrenes are, but each polystyrene can occupy n number of lattice. So the scale of the volume will need to be takes up how many number of lattice sites. In this case, it's going to be V0 and M2. So this comes into conclusion that your volume fraction for the solvent is going to be equal to M1 divided by M1 plus N multiplied by M2. And in other case, phi 2 for the polymer's volume fraction will be number of degree of polymerization multiplied by how many numbers of the polymer there divided by total volume. So in a unique special case, when your polymer is short enough, when n equals to 1, your Flurry Huggins is downgraded to lattice theory. Okay? Then this will be exactly the same as x1 equals to m1 plus n equals to 1, so it's just m1 plus n2. Same here. Okay? So now the tricky part is, now how do we understand the entropy? The statement is there. The mixing of a polymer in the solution is now going to be more difficult. In this case, when we fill in solvents, it's going to be the same. But when we fill the polymer, it will be different. When we fill it, the first one you can fill number of total of possibility is given there, right? So the connectivity is start to make an impact on your polymer's entropy. Okay, so how do we address this problem? As stated here, the possibility of neighboring site already being occupied becomes a major problem, right? So we cannot say, when we have a connectivity, we cannot fill back in a few spots as already at. Anyone want to give a guess? It is indeed a very hard question. Even in textbook, if you read Ting Lodge's textbook, it's very hard to directly using the theory to compute what is the entropy for the polymer. So we're just gonna be taking some approximations to understand what would be the entropy. Okay, so in this part, it's basically the same as stated in lattice theory. Everything we learn from lattice theory can still be applied into Flurry Huggins theory. So you can still understand what is the entropy change with respect to the understanding how much number of different states sigma is. So it comes down to we need to understand what is possible states in sigma. Okay. So how do we understand that? This is given by this particular equation. So in the homogeneous mixture of component 1 and 2, you have a number of states is given there. The total number of lattice sites occupied by species is going to be total number of states multiplied by phi 1. So how much volume fraction you have in that particular case, phi 1. Okay? So phi 1 is basically the volume fraction. And L is total number of states for the system. And we quickly will learn, if we use that simple relationship, we can understand the entropy on the mixing can be given by this particular equation, delta S mix 1, delta X mix 2. This is with respect to the different component in it. S1, S2 mixing states inside the mixture for your polymer and for your solvents. This will give you the overall mixing states, which is given by the following equation. If you read the final conclusion, this will be similar to what we have talked about. The total degree of mixing after mixture will be equals to minus R n1 log in phi 1 plus n2 log in phi 2. It's very similar to lattice theory for now, okay? The change of entropy for the system. But the differs start to deviate when we look at the top. The delta of mixing in this will be considered into the phi 1 and phi 2. In the lattice theory, it's considered x1, x2. These are with respect to each individual state. This is volume fraction. This is also volume fraction. But because of phi 1 and phi 2 are defined differently, if we normalize the lattice sides, okay, this is a total system, but we have normalized by per lattice sides, which means we need to divide everything by n1 using this equation. If this is divided by n total lattice sides, okay, again, n is defined by how many solvents, how many polymer, multiplied by degree of polymerization. We will reach this conclusion. Per sides, delta S mixing will be equals to K phi 1 log in phi 1. How do we get phi 1? N1 divided by N is exactly as phi 1. Okay, there is no question about that. Now, how about here in the lattice theory, we don't have n term. Why there's n term in terms of Flurry Huggins theory, where this n comes from? So when we consider an entropy term, n2 divided by n, n2 divided by n1 plus n2 is not equals to phi 2 because we are missing n term here. So this where this n is start to show up if we normalize per lattice sides and log in phi 2. Okay, so in lattice theory, delta S equals to minus K x1 log in x1 plus x2 log in x2. In Flurry Huggins theory, now you realize the contribution of the polymer in terms of its entropy in mixing is unchanged, right? It will be the same to the system. However, the other half of the polymer contribution in mixing is lowered. It's lowered by a factor of n. So how do we understand? If n is equal, if the degree of polymerization is 1,000, that means the contribution of entropy for this polymer before and after mixing will be much smaller than solvent contribution, right? If phi 1 and phi 2 are both 0.5, this will be bigger than this by a factor of n. N is easily 1,000. So this means polymer mixing for the polymer component doesn't contribute much to mixing. Why? Because think about in entropy, how much changes for the polymer entropy before you mix them in the solid state, it's already connected. And in the lattice, after it's mixed solvent, there is just not much change in terms of connectivity, conformation. So your disorder doesn't change a lot for polymer. I would like to slow down here a little bit. Let me emphasize one more time. Your polymer doesn't contribute a lot, okay? So a natural extension of this for polymer-polymer mixture will be easy to understand. You can apply the same theory and argument that if you consider a polymer 1, polymer 2, this will be phi 1 divided by n1 and phi 2 divided by n2. n1 and n2 are degree of polymerization for polymer both. If you see this, you will see entropy is always favors mixing. When we replace a solvent with a polymer, what we did to the system is we lower the entropy contribution from polymer. As we did in the last calculation, we know this is roughly minus 0. Let me make sure I get that right. Minus 0.693. That's contribution of toluene, that's contribution of hexane. If we replace with the polymer, with degree of polymerization, let's say 100, this term going to be 0.00693. You don't have much contribution anymore from the polymer. So when you combine together, your entropy will be lower, although it's still going to be higher than entropy in this case, even we X away this part. But however, let's go another thinking. When we mix two polymers, both has dP about 100, then this will be 0.07 roughly. This will be 0.07. Then the entropy finally going to win the game. Says, oh, there's not much entropy gain when you mix two polymers, so they're not going to mix. I will deny the case, and it will be phase separate. Okay? But as you can see, the entropy is always favors mixing, but in the case of polymer solvents, your entropy is less stronger to propose the system to mixed state. So when your chi is high enough, it will phase separate. And this is a typical comment in many high molecular weight systems and with unfavorable interaction. So we have covered this part. So how about in the Flurry Huggins theory, how about contribution in the entropy? We talked about entropy contribution. How about entropy? Entropy is just considering the pair interaction. It's actually very similar in both cases. The connectivity doesn't impact the pair interaction function. We just need to count how many monomer units in solvent and how many monomer in polymer and consider. So in the regular solution results or regular lattice, we have M1, number of toluene, X2 volume fraction, chi parameter, and KT. In here, we just need to replace X2 with the phi 2. In this case, this is going to be given by volume fraction of the minor components, okay? But the connectivity doesn't make as big impact here. Okay, why? Because you can still consider the pair interaction between your polymer with a neighboring lattice. We did make one assumption is, despite the connectivity, there's still quite some sites it can interact with solvent. So it can either contain with the solvent or monomer. We do took approximation, but it doesn't impact our final results. So here reaches, I think the beautiful part about polymer physics is now we can talk about free energy for polymer solvents mixture. Flurry Huggins series, this was proposed by one of the giants in the field, P.J. Flurry. As we see here, the top defines what is degree of mixing in the case of you have a solvent. Okay, so this is a total system. This is per lattice sites. The difference is it's normalized by lattice size number n equals m1 plus n multiplied by n2. And this is the most commonly you will see in many textbook or homeworks or theory. This basically says per lattice size is, if you look at individual lattice sites, the average energy delta G of mixing will be equals to KT multiplied by phi 1 log in phi 1, contribution from solvents in entropy. Phi 2 divided by n, we talked about the connectivity of the polymer lowers the entropy, and it's reflected here, log in phi 2, and plus the entropy contribution is phi 1, phi 2 chi. Okay? This equation has been the cornerstone for thermodynamics of the polymer in the last 5 decades. It can be used to predict a phase diagram and understand osmotic pressure. And we will talk about phase diagram in the next lecture or two. Phase diagram is basically based on this equation. You give me a polymer, you give me a solvent. just using this simple equation and understanding chi, I can tell you if I mix the polymer at this concentration, will it be phase separate or mixed? Phase separate means, in that case, if you have phase separate polymer and solvent, it means polymer will not dissolve. It will be happily becoming two-phase, which is a layer of precipitated polymer at the bottom of your solvents, if polymer is heavier than solvents. If they're phase mixed, means they will be homogeneously dissolved. You have a polymer chain form a good solvent and swimming around in the lattice of your solvent. So they're fully dispersed in that case. We will be able to construct the phase diagram for polymer and for any given solvents, as long as we know chi value, right? This is an unknown factor. Chi will make a huge impact. So let's think about a few scenarios. What if chi is bigger than 0? Chi is a positive value. That means there's repulsive interactions between your polymer and solvents. Okay? The polymer prefers to assemble, the mixture component prefer to just stick with itself. So in this case, if the polymer can be dissolved depends on specific scenarios. Because as we showed in the example of polymer solvents mixture, when the chi is positive, this phi 1, phi 2 is going to be positive. So entropy turn is not favored for mixing, but it needs to have a battle with entropy and see who wins out. So it's unknown. Depends on specific scenario. But in the other two cases, let's say your chi equals to 0, then this second term will be equal to 0. And then, as we know, entropy is always favors mixing. So you're always going to have mixture. Your polymer is always going to dissolve in solvents in this case. Of course, if you have a negative chi, it will be even better, because then your entropy favors mixing, your entropy is also favors mixing. Okay? So that's a few scenarios. And we will talk about later how to, we know that chi is so important. It's very important to get accurate chi and measure the interaction parameter between your polymer and solvents. So it's indeed is important, and we will talk about how you can measure them experimentally, or you can rely on some polymer handbooks to get this chi parameter. You don't necessarily need to measure. Of course, if you made a fancy new polymer, nobody has made it before, you need to measure it, because you can't look it up in the handbook. But in most of the scenario, polystyrene, polyethylene, those material people have already measured. You can find what the chi value. If you know the chi value, you should be able to estimate where the polymer mixed with solvent or how the phase behavior. Okay? So any questions so far for an evolution of the lattice theory? I think if you understand lattice theory, Flurry Huggins theory is pretty straightforward as well. Any question? Okay. Looks like everybody is doing well. So I think then everyone should score 100% in this quiz test. All right, if no more questions, we can probably, let me see the time. We can chat a couple more minutes. I'll tell you what we're going to do in the next few lectures. Okay, great. We can show an example. So this is an example. So this example is asking you to compute, what about polystyrene with a molecular weight about 10 kilodalton? Is dissolved in cyclohexane at room temperature, yield 10% solution by volume. And let's see what is free energy change delta G. We have given you a few things. We give you the volume fraction. We give you the molecular weight. So this is going to be important. And we need to give you another assumption, that is, in the theta condition, chi equals to 0.5. And I'll talk to you later. For now, you just need to, unfortunately, memorize it. What chi equals to 0.5 is a theta solvent. This is a definition, okay? So you can think about chi will be given in this question for 0.5. So we know the chi volume fraction, molecular weight. This should be a fairly straightforward science case, right? You apply the Flurry Huggins equation, you should be able to get what we want to show here. Okay, so how do we address this problem? First is we need to get what is the phi 1 and phi 2. This is not has shown, or M1 and N2. We have shown, we know there is 10% volume will be given by the equation. So 10% will be phi 2. This is polystyrene. Phi 1 will be 0.9. So how about M1 and N2? How do we convert the volumes to how many number of molecules? So that requires to convert unit volume or the density. You can convert how much unit volume per mole. So you can use the volume to convert how many moles to how many molecular. Okay, this is shown here. We assume for it's 1 cubic centimeter, so among that there will be 0.9 cubic centimeter for solvents, divided by how much solvents in this unit for this amount of volume. You can get how much moleculars for the solvent hexane. Number of mole, Avogadro number, so this will be give you the M1. Okay, and you can apply the same approach to the polymer to get M2. It's not too surprising. Your polymer is much less, just because each polymer is pretty long. Okay, and you only have 10% of polystyrene. So use that, you can calculate the delta G solvents. How many number of that? This is Avogadro constant multiplied by T is the temperature. How many number of molecular? Law in volume fraction. Number of polymer, volume fraction, and multiplied by number of solvents, volume fraction of polymer, chi parameter. They will give you the delta G for the system. Okay? So the delta G basically says it's a minus 1.24. And we know the polystyrene will be happily dissolved in cyclohexane. Okay? So you can apply similar questions to other systems, other solvents. Pretty useful, I would say, in a practical use of this Flurry Huggins theory. So I'm going to stop here, and in the next lecture, we're going to start to cover next topic. We can either cover the polymer solutions to look at how does osmotic pressures can be tied into Flurry Huggins, or we can look at the phase diagram. I'll take a look, see which fits the best. I'll assign some homeworks in the again in the channel in the Canvas. So I'll go and take a look again and assign a few homeworks for everybody to practice the Flurry Huggins theory knowledge. Okay? And any question for me today? If not, then let's finish today's lecture. Okay?